Hi, so in this little clip we're going to have a look at how to perform a manually calculated or stepwise t-test calculation in Excel. So the sample we have two samples on the left hand side for flowers, petal lengths, two sets A and B. So samples are taken from two different types of flowers to establish if both varieties have the same petal lengths. And the first thing we want to think about is what are our tests of hypotheses. So our two hypotheses are here shown on the screen. The null hypothesis is that mu1 equals mu2, that there's no difference between the populations, or the petal lengths of type A and type B are the same. The alternative hypothesis is that x bar is not 1 is not equal to x bar 2. There is a difference between the samples. The petal lengths of type A and type B are different. So the first thing we have to do is check to see are the variances of the two samples similar. And the way we do that is to use an F-test. To carry out the F-test, we first have to calculate the F-statistic, and that's given by this formula here, the larger sample variance over the smaller sample variance. So I'll just add in a few more formula here to help us in our calculation of the two sets of variances for the two samples. So you can see here that the variance formula is the sum of the individual deviations from the mean divided by n minus 1. That's for sample variance. And I've added in the sums here and the number in each. There's 25 in the first in A and 24 in B. And that allows us to calculate x bar for both 2.99 and 2.79. So next we want to calculate the set of values for x minus x bar for A. So you can see I've added in a column here x minus x bar for A, and each calculation is the individual x, which is 3.2 in the first row case, minus x bar, which is the value we calculated on the bottom, 2.99. You'll also notice here that we've used an absolute reference for the x bar, because as I move it down, if I pull it down, the values, as I'll show you here, we can see that the same x bar needs to relate to the whole, all the samples. Our next step is to put in a column for x minus x bar squared, in which we square each of these single values. So I've color coded two columns here just to make it clearer which is A, and we've done the first calculation here, which is 0.21 squared, and then I'm going to use the autofill function in Excel to fill in the rest to get all the values of x minus x bar squared for the sample A. So after that, our next set is to do the same thing exactly for sample B. So you can see I filled in all the values for sample B and color coded those as well, and you can see the sum for those is 2.1. Now in both cases we get the variance by dividing by n minus 1. So if I just look right in here, you'll see that it's that formula is the 2.1 divided by the number in the sample for B, and similarly with the sample A. So we've got both sets of variances now here along our bottom row, and we can now go on to calculate the F statistic. Our F statistic calculation is given by this formula here, which is the larger sample variance over the smaller sample variance. So in our case that gives us this value here, 0.125 over 0.091, and overall that gives a value of 1.3694. Our degrees of freedom are 1 less than the number in each sample, so 25 minus 1, 24, and 24 minus 1 gives 23. We've set our value of alpha equal to 0.05. So we're now in a position to go and look up our F table to determine our F critical value. To determine our F critical value, we look up the table for alpha equal to 0.05, which is our appropriate level. We look along the columns for the highest variance, for the sample with the highest variance, which in our case was A with 24. We look down that column, and using the DF2 is that with the smaller variance, which is 23 in our case. So the intersection of those two figures gives 2.005 as our F critical value. We can see here that our calculated F statistic 1.3694 is less than our critical statistic 2.005. So that implies we're not in a position to reject a null hypothesis. So we have to assume that there are equal variances, that both samples have equal variance. And there's a chart of the F distribution, and we can see we didn't get into the rejection zone, so we're in here. So we then, as I said, have to accept that the variances are now considered equal. And we'll move on then to look up the formulas for the equal variance situation for calculating a t-statistic. So here you can see the three sets of equations that we need to calculate our t-stat and also to calculate the degrees of freedom. So it involves the calculation of a pooled variance value, which is given here by this formula. And we'll go on then to calculate each one of those in turn. So you can see here I've laid out the calculations. One thing of particular interest or note is that mu1 minus mu2, we're going to assume that both populations have the same mu, so we can mu1 minus mu2 goes to 0, so that effectively drops out of our equation, so we don't have to include that in our calculations. So we've calculated here a t-statistic of 2.12879 and our degrees of freedom are 47. So we're now in a position to go on and look at the t-tables to see what would be our t-critical value. Here we have our standard t-table, and we've chosen earlier that alpha is equal to 0.05. So we look along here, it's a two-tailed test because we said equal to or not equal to, so it's got two tails. So we look across here to 0.05, which is the appropriate column for us to look up. And our degrees of freedom are 47, which lies between 40 and 60 here. So roughly speaking, our value is between 2.021 and 2.000, so roughly 2.01. So we can now go back and compare that to our calculated value. So our t-critical value from the table is 2.01 approximately, and our calculated value for t-statistic 2.12879. So what does that mean? If we look at the t distribution, we can see that our 2.12879 falls just inside the rejection region. In other words, it's greater than the t-critical, which is 2.01, which would be the zone, the point where we enter the zone. So on that basis, we can say that there is convincing evidence to reject the null hypothesis. Overall, we can say there's convincing evidence to support the alternative hypothesis that there is a difference between the means of the two samples. In other words, that the petal lengths of the two flowers are different. So here on this worksheet, I've laid out our statistics that we've calculated on our steps. So initially, to calculate whether there was variance or any different between the two samples, we calculated our F statistic at 1.37. The degrees of freedom are here 24, 23. We set on alpha equal to 0.05 as an appropriate level of probability or significance. Our F critical from the table using those values is approximately 2.01, and that allowed us to say that we could consider the variances of the two samples to be equal. That led us on to a set of formula to calculate t statistic, which was 2.12879, degrees of freedom 47, and looking up our t tables, we were able to establish that our critical value for the t was 2.01 approximately. So overall, there was convincing evidence to support the alternative hypothesis that there's a difference between the means of the two samples. The petal lengths of the two flower species are different. So having done that, then we might like to have a look at our data analysis tool pack in Excel to see does it confirm our figures. And if we start with our F figures initially, the way we would do this is we click on data, and then we go over here to the right to data analysis, and we choose F test to sample for variances. Say OK, and then we need to put in our data. So our variable 1 range is this first column here, A. We select all of that, and our variable 2 is B. Now in both cases I've included the header, the A and the B, so because I've done that in order to alert Excel to the fact that the first row is actually are not measurements but titles or labels, I click this box here, labels. Our alpha is 0.05 as we've already chosen. So the output range is where we're going to put it. So we're going to put it in our own sheet here. So I'll just click into this box and then pick a zone here, let's say here. And then next all I need to do is click OK, and Excel will generate the statistics for us. And we can see from that the statistics are very similar to ones that we calculated ourselves. Having confirmed our figures for the F-test using the Excel data analysis toolpack, we now want to check to see if it also agrees with our T statistics calculations. So to do that, we go again to data here and then data analysis, and we go down to t-test, and it's t-test to sample assuming equal variances, which we established using our F-test earlier. So we say OK, and now we need to fill in the various boxes much as we did before. So we're going to select A and then B, and again we need to click, it's already clicked the labels button to alert Excel to the fact we've used the full set including the heading. So next we want to position it somewhere, so we'll say output range and we'll click here. I just move this over out of the way and we'll put our data output here, our statistics output here, and now we can say OK, and Excel has generated a set of statistics for us. We can see they're very similar to the ones that we calculated ourselves. So now we've concluded what we wanted to set out to do, which was perform a manually calculated t-test in Excel for unpaired or independent samples, and then checking our outcome with the Excel data analysis toolpack. So now that's our work is complete at this point.